be talking about simulating ocean eddies and developing and evaluating viscous versus backscatter and backscatter parametrizations. So it's not purely backscatter, it's also viscous parametrizations in the ocean. This is some work together with Sergey, Danilov, Katya, Ekaterina Bagaeva. It doesn't work. Doesn't work there. No. And Anton Kutsenko and Marcel Oliver. So all of them actually are participating in this workshop. And Marcel is going to give a talk tomorrow, and Katya is going to present a poster. So what I'm showing in the bottom here is actually the same simulation of an ocean model at eddy permitting resolution, which is something like 25 kilometers, once with a backscatter parametrization and once without. And this is ocean velocities at 100 meters depth in terms of absolute velocities. And you can see by eye that once I switch on the backscatter, it just becomes much more turbulent. You see a lot more of these eddy structures. And ideally, what you want to see is also that, can you see this pointer actually? No, it doesn't mirror. Okay, but it should mirror on the, at least for the online people. What you can see is that the Agulhas rings, for example, tend to show up more clearly. Also, the Malvinas current tends to have this more horseshoe pattern that it's supposed to have. So it seems to be going in the right direction. Just as an overview, I mean, we just heard this talk by Rosie talking about something like between 0.5 degree and 1 degree, where you have this non-eddy resolving simulations where you're trying to actually mimic the effects of the eddies completely, which you usually use the Gent-McWilliams parametrization and then some ready diffusion and some eddy viscosity. You can have these eddy permitting simulations that we will be looking at, which is between 1 degree and 1/10 degree, where the Rossby radius is not quite sufficiently resolved, but partly resolved. Then the question is, do you still use GM? Don't you use Gent-McWilliams? And what do you do with the eddy viscosity? And then you have what is called the eddy resolving ones, where we hope that all of the eddies are actually properly simulated and you only have some remaining viscosity that sort of mimics the downscale transfer of energy. So what we will be focusing on, what I'll be focusing on, is this eddy permitting regime. Just to highlight this again, it's basically on the left here. So this is different resolutions with this ocean model that we're using at the Alfred Wegener Institute, which is also part of this Transregio set of models that is being used. On the left-hand side is the eddy permitting 25 kilometers, and you can see as you move towards eddy resolving on the left, on the right with the 4 kilometer, you start to get more and more eddies in the flow. And again, this is absolute velocity at 100 meters depth in terms of the white color scaling there. So a classical bias that you have in models, one was shown by Jenny, which is this North Atlantic bias, but you also have a bias in terms of sea surface height variability. So this is sea surface height intermonthly variability from Aviso sea surface height measurements or sea surface anomaly measurements in this time period. And usually this is the bias that you have. So this is the bias in terms of a relative bias. So the observations divided by reference simulation at a 1/4 degree, and red basically means that you're underestimating sea surface height variability by up to a factor of 3. So you're strongly underestimating sea surface height variability, especially in the western boundary currents, Kuroshio, Gulf Stream, Malvinas Current, Agulhas retroflection zone, and in the Southern Ocean. I will skip over this. This is basically the model that we're using. This is the FESOM ocean model that is using triangular grids. So you can see this, I think, in this picture down there a little bit. And the basic idea, and this was mentioned this morning in the last talk, that actually one of the things at this resolution, which is quite tricky for not spectral models, but actually for finite, for grid-space models, is that you want to have as little energy dissipation by your numerics and by your viscous closure as possible, but still keep the model stable. And that sort of poses a big problem. And usually you are over-dissipative, and that affects the eddy production. It affects the eddy lifetime. And it sort of drains too much energy out of the system, especially at eddy permitting resolution. So, and now I just briefly go through what I mean by viscosity parametrization. I mean, again, this was also mentioned before, but this is your momentum equation. And on the right-hand side, basically, is your parametrizations. On the left-hand side is all your dynamics, so Coriolis force, advection, and so on. And on the right-hand side, you have some operator V, which is your viscosity in the horizontal, and then you have a vertical viscosity as well. And there's various options how to parametrize this viscosity, which is classical closure that is down gradient in a sense, so you dissipate energy. You can choose in terms of whether you want to use a harmonic or biharmonic, so Laplacian or bi-Laplacian operators, or even higher order, as we heard already. Also in spectral models, you can go easily even higher than Laplacian squared. You can use leaf viscosity. So once you have the operator, you have to fix the coefficient of viscosity, so the local strength of viscosity, and you can go something like leaf. We also have this option, what we call upwind type viscosity, because it goes in the direction of upwind advection, which is basically scaling with the absolute velocity. So the higher the velocity, the higher your viscosity coefficient. And then we came up with this new scheme, which is a viscosity coefficient that is based on the absolute difference. There should actually be one less here. It's the difference between neighboring cells. So it's the difference in the velocity between neighboring cells. So something like a gradient in a sense. And that is especially effective on these triangular grids that we're using as a viscosity. And now I go back, forward. Now with backscatter, the next step is basically that you add another term. So we heard this in Jenny's talk. So basically you have a viscous part and then you have an anti-viscous part. So that re-injects energy into the flow, and they together act as a new parametrization that is supposed to reduce energy dissipation at large scales, but have strong energy dissipation and especially entropy dissipation at the very smallest scales close to the grid scale, so that you have a strong drop-off of energy just right at the grid scale, potentially. And there, again, we have different parametrizations for this. We've developed something that we call kinematic backscatter, which is just a combination of a viscous closure plus alpha times the viscous closure filtered. And this alpha now is negative, so it's an anti-viscosity. And the filter, that F there in this equation, just takes care that we re-inject the energy on larger scales. So filtering makes the scales larger, so we re-inject on larger scales. What is happening now? Okay. Does it work? Yeah. So that's one way to do it. That's a very numerically driven one, because now we're just trying to locally compensate too much energy loss at large scales by re-injecting this energy. So this is numerically driven. But then we also have something that is probably closer to what actually Jenny showed, which goes back also to ideas by Eden and Greatbatch and so on, to have something like a subgrid budget, where you actually keep track of how much energy you dissipate at each time step locally. So this is this dissipation rate. You put that into the subgrid energy budget, and every time you backscatter some of this energy, you re-inject this energy back into the flow, but you remove it from the subgrid. So this E there is the subgrid energy budget. So at each location, at each time step, you keep track of how much energy you're losing in the system and how much energy is then available for backscatter. And this gray arrow there mimics the part that actually dissipates properly, which of course needs to be parameterized by the C-dis parameter. So some energy is actually being transformed away from kinetic energy, and that needs to be dissipated in this scheme. And of course, the way this all works then is that the subgrid energy budget defines your backscatter coefficient. So the more energy you have in the subgrid, the more energy is available for backscatter, the more you can re-emphasize the flow. So the general idea here is that you have a sort of numerically driven idea where you want to reduce over dissipation, but you coupled it to something that's sort of physically keeping track of how much energy is actually available for backscatter. So it's a mixture between something that's numerically driven and something that's physically driven. Of course, this, again, there's a lot of things that might need to be parameterized. For example, how much energy is actually physically dissipated. And also, Ekaterina will show on her poster that we can add further terms. So here it's really just how much energy is leaving the system, how much energy is being re-injected, plus some diffusion, but there could also be advection, some stochastic parts, and that is what Katja will show in her poster. So what we do now is we use this in a model setup, first in an idealized setup. This is the so-called souffle test case that we used from Souffle et al. From 2016. Different resolution. It's a re-entrant channel, so it flows from left to right. What goes out to the right comes back into the left. And you have some relaxation of isopycnals to keep the flow baroclinically unstable, basically, but retain a mean flow that goes from left to right. And you see at 20 kilometers, we hardly have any eddies, especially in the vorticity field. You can see this, while at 10 kilometers, we see these filaments and eddies are developing. This is a very busy slide. I just wanted to show this. to show you the range of what you can achieve by changing viscosity and backscatter parametrizations. So let me go back. Can you actually see the mouse? Yeah. So what you can see here, this is a eddy kinetic energy profile. So in the top, this is the surface, in the bottom, that's the bottom of the basin. And you can see that there's a lot of kinetic energy in the surface and little kinetic energy in the bottom, and or eddy kinetic energy in this case. And the black line here, that's the classical upwind viscosity that we used before. And then as you move to the right, you change first the amount of backscatter that you perform with this kinematic backscatter. When it says 0, it's basically a harmonic backscatter. Then this is biharmonic, and this with 0 is basically still viscous. 1 is also still viscous, and only at 1.5 it starts to actually effectively backscatter energy into the flow. The reason why it moves to the right, even for 0 and 1, is that we change the viscosity coefficient. So by just changing the viscosity coefficients to this local difference in velocities, we just have less energy being dissipated by the viscous closure. We get more energy into the flow, and therefore the kinetic energy moves to the right. So just changing the viscosity parametrization already helps quite a lot in energizing or keeping the flow energized. And then if we move to the blue line, which is actually now with backscatter, proper backscatter, we can actually go all the way to the right here. So this just illustrates if you use different parametrization for viscosity and what happens with that. And then we also looked into the spectra. So again, here, this is now the leaf parametrization for viscosity is, so this is eddy kinetic energy spectrum. And the backscatter one is the blue line on top of that. So you see, we re-inject energy on all scales. And Jenny also showed this. We basically lift up the entire energy spectrum. And what you see on the right is that's how backscatter basically functions. So this is so if you look here, this is the viscous plus backscatter closure. And if you scalar multiply this with U, then it's the dissipation power. So this is the actual dissipation power distributed over scales that you can see. And if it's negative, it means we drain energy out of the system. If it's positive, it means we re-inject energy into the system. And you can see the orange line is dissipative on all scales, the leaf parametrization. And it actually has a lot of energy being drained out of the large scales, so to the left of the plot. While the blue line is the backscatter one, it takes out energy quite a lot on the smaller scales, but it re-injects some of this energy or a lot of this energy into the large scales. And by that, it overall is a lot less dissipative than the orange one. And especially, it doesn't interfere with the large scales so much anymore. It doesn't drain energy out of the large scales. Yeah, and this is just a simulation now, again, with backscatter, just to show you what happens. So on the left, you can see a classical 25 kilometer resolution viscosity parametrization simulation. On the right, you can see it 8 kilometer simulation, so eddy resolving. So the right you want, the left you get. And if you put on backscatter, then the left one suddenly becomes a lot more variable and looks much closer to the high resolution simulation. And you can also see this here. So left is 25 without backscatter, right is 25 with backscatter. And in the middle, you see the eddy resolving reference where we want to get in the end. So we can get quite a lot closer to something that is a lot higher resolution just by taking care that we don't lose a lot of energy during the simulation. Looking at the biases for global simulations, again, what you can see here is the Aviso sea surface height variability. You see the regions where there should be a lot. In the bottom, you can see where the biases used to be. Where it's red, we just had way too little variability because we are missing the eddies. And on the right, you can see what happens if you switch on backscatter. A lot of these red blotches just disappear or at least get substantially reduced. And that actually is what you expect because we have more energy in the system. So locally, we actually can get up to more than 40% reduction of bias in some regions, but globally, it's about 10% reduction of bias. But more interestingly, actually, and that again goes back to Jenny's talk, is that we also see that the mean flow changes. So it's not just the eddy variability that increases. So again, in the bottom, this is the reference without backscatter, and on the right, it's with backscatter. In the top, it's Aviso. This is South America that you can see there on the left. So it's the Malvinas current. And you can see when we switch on backscatter, actually the mean current also is able to get more of the colder water being propagated to northwards as it should be, while in the reference this doesn't happen. So also the eddies help to improve the mean flow. And again, this was also discussed by Jenny in the other talk. And we see this for other currents as well. So just you can have a look at that, but it basically is pretty much for right is Gulf Stream, then comes Kuroshio from the right, then it's the Malvinas, and the bottom and the left one is the Agulhas current. And in all cases, the top row is much closer to the middle row, which is Aviso, than the bottom row, which is without backscatter. And just to show general statistics, so if we look at bias reductions for the dynamic part, then we can see that sea surface height mean biases actually go down globally by 10%, but in some regions like Agulhas current, even up to something like 20%. Sea surface height variability biases go even down to something like 40% reduction of bias. And the nice thing is that, and again, going back to the talk, 2 talks before, that we also are able to reduce some of the temperature biases or salinity biases. And you can see that in the bottom, global surface biases and salinity bias get reduced by something like 10% globally. In some regions, it's much stronger. For example, in the Indian Ocean, if you cut a transect through the Indian Ocean, the reduction can be up to 30%. And that brings me to the end, and I think I'm about in time. So I've sort of skipped a bit through different topics here, but the main idea is that kinetic energy backscatter leads to large improvements in variability, but also in the mean flow and water mass properties. We do have different options. We have this very simplified backscatter, which we call the kinematic backscatter, which instantaneously re-injects energy to just make reduce some of the issues that we get due to numerical over dissipation. While we have this dynamic backscatter, which has the subgrid energy budget to make it more physical. So, but it's also more costly. So you can choose basically between efficiency, flexibility, physical realism, and so on between these schemes. Then we have also an improved viscosity coefficient, which also leads to less dissipation to start with, which is really good. And finally, we are using quite extensively these idealized settings, so this channel flow, to actually look more closely into spectra and try to understand more clearly what happens actually with also, and you will see this also with the work that Ekaterina is doing, how to add new compartments to the subgrid budget and so on, can be really nicely tested in these idealized settings and can be compared to other simulations then. And that's all I have. Thank you very much.